Okay, welcome, Fanny and Alexi and Rigny and Stefani, Alexis, Susanna, and Tony, Diego, and Adam. Thanks for coming. Let me jump to that quiz. Okay, so here's your quiz. We have f of xy equals x squared y minus 3x plus y minus 5. And we have u is 4/5 comma 3/5. And the first question is find the gradient of f of xy. All right, so for that first question, how do you find the gradient?
Take the partial derivatives.
Yep, you take the partial derivatives. So grad f is equal to, so what is the partial derivative of f with respect to x? Shouldn't be too hard.
Uh, 2xy
2xy minus 3.
Yep, 2xy minus 3. And what is the partial derivative with respect to y?
X squared plus 1.
Yep, x squared plus 1. Any questions on part A? Okay, let's go to part B. Part B is find the directional derivative of f at x of f evaluated at the point -2, 1. Okay, so to find this directional derivative evaluated at that point, we could do it the hard way or the easy way, and I hope you guys chose the easy way. What's the hard way of doing this?
The limit definition.
The limit definition.
Das Limit.
Okay, let's hope you didn't do that. Okay, I mean, if you got it right and you did it that way, I wouldn't count you wrong, but then you're just masochists, I guess. Instead, what's the easy way of finding the directional derivative? We plug in -2, 1, but we got to do more than that. So that would be, if we plug in -2, 1, that would be just the gradient at the point. We don't want the gradient, we want the directional derivative. Yeah, we take the gradient of f, and then we dot it with the vector u. Okay, any questions on that? Okay, so the gradient of f, again, we've already done that in part A, is 2xy minus 3, comma x squared plus 1, but we have the point -2, 1, so I got to plug in -2 and 1. So if x is -2 and y is 1, you get 2 times -2 times 1 is -4, minus 3 is -7, comma, and then again, x is -2, -2 squared is 4, plus 1 is 5. And then we're supposed to dot that with u, and u was 4/5, comma 3/5. Any questions on that? Okay, and then we just do it, and we get what, 28/5. In fact, I'm going to factor out the 1/5. It's easier. Little rule of dot products, you're allowed to do that. You can factor a constant from either of the vectors. And then we get -28 plus 15. So -7 times 4 is -28, plus 5 times 3 is 15. -28 plus 15 is -13. And that's equal to -13/5. Any questions on finding the directional derivative in the direction of a vector given a point and the function? Okay, so part C is find the maximal directional derivative of f of xy at the point to -2, 1. Okay, and what's the big theorem about the maximal directional derivative?
It's the magnitude of the gradient.
Yeah, so what we do is we find the magnitude of the gradient. Okay, let's go to C. Okay, at the point -2, 1. And we've already found the gradient. So the gradient is -7, 5. How do we find the magnitude?
You square root
Mhm.
the -7 squared plus 5 squared, which gives you square root 7d4.
So we're going to take the square root of -7 squared is 49. And then plus 5 squared is 25. And you get the square root of 74. Any questions at all on this quiz? Any questions? If you know what to do, it's a little shorter than normal quizzes because it's all there is to it. I could have asked you a limit definition one, but I said not to. But any questions on kind of finding the gradient and finding the maximal directional derivative and all that? Okay, if there's no questions, then I'm going to move to the new stuff. But before I do that, let me ask you, are there any questions about anything?
Yeah, I have a question about a couple of the homework problems.
Mm-hmm.
So there was number 11 through 13. The prompt was to find the unit tangent vector to the level curve at a given point that has a positive x component.
Uh-huh.
And it took some doing. I've watched a few videos. The Math is Power for You link that's provided did not really help with that. Yeah, that's the thing. Switching the answers, like you switch the x and the y component, and then sometimes one of them would need to be
Okay, so let me go through the
inverted
steps.
from where it is.
Let me go through the
Okay,
steps.
yeah, thank you.
Step 1 is find the normal vector. Okay, so find the normal vector. Now, how do you find the normal vector to a tangent plane? Because that's my guess is that's the one you probably tried first and without really closely reading the question. And what'd you do?
Yeah, just the straight normal vector is the gradient of the
Yeah.
function.
So that's grad of f. Okay, at the point. Okay, now notice the normal vector is not the unit tangent vector, right? But we had a theorem that said that the normal vector is perpendicular or orthogonal, whichever word you like, to every unit tangent vector on the plane. Do you remember that? So that was a big theorem we had. So step 2 is find the vector orthogonal to grad f. Now, how do you find a vector orthogonal to grad f? So if you had, say, the vector, say, a comma b, how do you find a vector that is perpendicular or orthogonal to a comma b? Not reciprocal. It's a good try, though. It's negative b comma a. And notice that works Because if you take the dot product, what do you get? You get 0, right? You get negative AB plus AB, and that's 0. So that always works in 2 dimensions. 3 dimensions is a whole different thing, but in 2 dimensions, it's very easy to find an orthogonal vector. Any questions on the step 2?
Yeah, that's
Okay.
definitely what was tripping me up, because I mean, finding a unit vector from that point is trivial, really. So
Yeah. So step 3, there's 4 steps actually. Find the unit vector in the direction of, I'm just going to say step 3, step 2. And how do you do that? How do you find a unit vector in that direction?
you divide your vector by its magnitude.
Yeah. Divide step 2 by its magnitude. Okay, now it turns out there are 2 unit vectors orthogonal to any given vector. Basically, you can go up or you can go down. Does that make sense?
Yeah.
Right? If you're going north and I say, okay, now you need to turn so orthogonal to where you're going, I haven't given you enough information, have I? Do you agree? Because if you're going north and I say go orthogonal, well, you might head east, you might head west. Is that clear?
Right. Yeah.
So similarly, for any vector, if you want a unit vector orthogonal to that vector, there's 2 choices. So they told you that you wanted a positive x component. So if the x component is not positive, let's say negative, how do you make it positive? So it's very easy.
Multiplied by -1.
Yep. Multiply step 3 by -1. Okay. Otherwise, you're done, by the way, in step 3. That part should be an easy step. So that's a process in finding the unit tangent vector. Is that you find the normal vector and then find an orthogonal vector to it, make it unit by dividing by the magnitude, and then choosing the direction by multiplying by -1 if needed. Does that totally make sense, or is that still confusing?
So that cleared it right up. I mean, I did get through the problems by just sheer brute force, trial and error.
You just looked at what they did and how you were off, and then you just have no
Exactly.
idea
Yeah,
what
I
you're
looked
doing,
at
but you
like
just
what
made
the
it happen.
result was, and I was like, well, how does that relate to what I got? And then
Right.
and I was
Yeah.
not able to determine a clear pattern. That's why I was like,
So what you were right to
asking you
do
for
was
help.
what you were right to do was ask me. Yeah. So if you ever get a problem right on the homework, but you have no idea why it's right or what you did, you need help. Okay. Because it's going to kill you on an exam. Does that make sense? So it's good that you asked.
100% why I asked.
Yeah, it's really good you asked. And I let you know you're not the only one that asked. I had some people that asked during office hours and just email. So you're not it. Well, this was hard for a
Yeah,
lot of
I
people.
emailed because the video did not what the question was asking for.
Yeah, I
and I
think
was
the
like,
video
is this
just
the
told you.
wrong video? I think I emailed you if it's the wrong video for that question.
Well, the video gave you step 1, right?
Yeah,
And then didn't finish it
semi-related,
off. Yeah, then didn't finish the rest.
misleading.
But does this make sense now? You know why these steps are important?
Yeah, that all makes sense now.
Yeah.
Appreciate it.
And my guess, it was step 2 that got most people to not think about doing step 2. Okay, any other questions? Okay, if there aren't any other questions, I have a question for you, and I've been doing this pretty much every day, okay, or every lecture, is I want you to go back to your memories of first quarter calculus. And who remembers what a relative extrema is? Right? That happened in, I don't know, it might have been October, maybe November.
The maximum and minimum of a given function.
Okay. But what does it mean to be relative? Do you remember?
Local max or min.
Yeah. What does it mean to be local? Who remembers what local meant? Okay, not the only one. Actually, it could be the only one, and then it would still be a local relative extrema. Okay, yeah, within a given range, and not just a given range, within a very small range. Okay, within a very small range. And I'm not sure if you remember, but we often said within delta. Okay, you move that little bit delta, and then f of x is going to be the biggest for x within delta of that point. Any questions on that? Okay, another question I have for you. Again, this is review of first quarter calculus, and then we'll jump to what we're doing now and realize it's basically the same. Who remembers what critical point means? When do you have a critical point? Again, this happened like in first quarter calculus. Okay, the derivative equals 0 is one possibility. And what was the other possibility? It actually doesn't have to change sign, but you have to have the derivative 0. Or what was the other possibility besides the derivative 0? Here's a hint. Y equals absolute value of x has a critical point at x equals 0, but the derivative is not 0 at x equals 0. Yeah, the function might be not necessarily the function, but the derivative might be undefined. Okay, so the derivative is undefined. You get a critical point. All right, so that's just a little review of what happened in first quarter. And now basically we're going to take that review. We're going to take what you did first quarter, and we're just going to throw in a y. Instead of just f of x, you're going to have f of xy. So let me go through and talk about all this stuff that you've already done in first quarter. But now we have to talk about it in our new way of thinking. So now instead of y equals f of x, we don't have that anymore. Now we have z equals f of xy. Any questions on that? Because that's what this quarter is all about, or at least this first half of the quarter. Oh, you know what? I know this is off topic, but it's an important topic because I always want to make sure I remind you. There will not be a lecture on Friday. How come? The hint is we don't have a holiday. Yeah, midterm. Yeah, I like to call it exam because midterm usually means there's just one of them and there's a couple exams. Yeah, so this coming Friday. Okay. Yeah, so this coming Friday, 4 days from today, there will be an exam. Okay, and just a reminder about that exam is it will use Proctorio. So you definitely want to make sure that your computer can handle it. Otherwise, we have free computers at the college on loan. You don't get to keep it for life. You'll get to keep it for the quarter, though, if your computer doesn't work. But you need to deal with that. You need to let me know so I can let them know, and then you go pick it up. But just let you know that Friday will be the exam. Okay, so a week from today. Okay, so that's really important. Okay, so I always like to give the reminder a week before. Okay. So now that I gave the reminder, let's continue on. And we can say that if f of xy is a function now, two variables, then AB, the point AB is a critical point. So you no longer have a critical value. Now you have a critical point because we're in functions of two variables of f of xy. If, same idea, right? We used to just say the derivative was 0. But the way we're thinking about the derivative now is the gradient. So the gradient kind of takes the place of the derivative. When we had functions of one variable, now we're in two variables, we tend to use a gradient to represent the derivative. And that is a vector, okay? And if we take the gradient of f, evaluate at the point AB, you get 0, 0. Okay, you get the 0 value. Okay, or the gradient of f of AB is undefined. Okay, is this feeling similar to what you did in first quarter? Even though the notation looks different? Right, does this look normal?
Yeah, it looks similar.
Yeah, I mean, it's the same idea. I'm not going to prove it. I'm going to convince you in a little bit of it by like pictures, but that's not a proof for sure. To prove it takes a lot of work. Okay, you need epsilon delta kind of stuff, and I'm just not going to go there. That's what you do if you become a math major and take what's called real analysis. Then you reprove all the things that we don't prove. So any questions on this big definition? Okay. So here's an example. Okay. And in fact, let me ask you something. What do you think is going to be the hard part of this definition? When you're asked to find the critical points, what do you think the hard part is to find the critical points? What's your guess?
Is it a derivative?
No, derivatives are never the hard part of calculus. What's the hard part of calculus? Which rate approach is not that big a deal either. Any thoughts? What's the hard part of calculus?
Algebra.
Yep, the algebra. Okay, and I'm going to say algebra / trigonometry because sometimes you get trig functions in there too. But yeah, it's the algebra, and that can get hard. Okay, it can get so hard you can't do it. So now we're jumping up a level now that we're in functions of two variables, because now when we say the gradient of f is equal to 0, 0, what that's going to give you when you take the gradient of a function, you're going to get f sub x and you're going to get f sub y. So you're going to have the partial derivative of f with respect to x equals 0 and the partial derivative of f with respect to y equals 0. F is a function of two variables, right? The partial derivatives are each functions of two variables. So now we have a function of two variables equals 0, and then another function of two variables equals 0. And you have to solve two equations and two unknowns, and sometimes they're brutal. Can you imagine that? So just to let you know, solving two equations, two unknowns, when you have hard stuff like cosines and e to the x's and y's and stuff like that, it could be nasty. Any questions on that? So I want to give you a reality check because the example I give you isn't going to show you the evil part. But we're still going to have to do an example. So here's an example. Find the critical points of f of xy equals x squared minus xy plus 4x. By the way, by looking at this, just a note, do you know what this looks like? If you graph this, right? We know it's a quadratic, right? Huh?
I said parabola.
Well, first thing, it's remember z equals x squared minus xy plus 4x. So we're in the xyz plane, xyz space. So the answer is you don't. Okay, even that is hard. Even to look at it, at the equation and know what this is. Do you know what makes it hard to know what it is? Other than we know it's a quadric, but we don't know what kind. Yeah, the xy. So I don't know if you remember, but when are you going to learn how to decide whether it's a paraboloid, ellipsoid, hyperboloid, or something different? When are you going to learn that? Any guess? Definitely not today. But it was a good guess. No, you're not going to learn that until 5th quarter. We're in 3rd right now. You have another 2 full quarters, basically, of math before you can even get to that point. So we're not going to do that. But what we can still do is find the critical points, even though we don't know even what this thing looks like. Okay, so you can trust me that this won't happen until 5th quarter. So linear algebra, matrix theory. Okay, so instead, we're going to do what? If you want to find the critical points, what do we do? What do we have to find? And if you don't remember, let me pull up the definition. To find the critical points, what do we need to find? Yeah, we need to find the gradient. So let's find the gradient. Grad of f. Okay, it's not too hard. What's the gradient? So what's the gradient of this function? Yeah, so the first one, the partial with respect to x is 2x, and then minus y plus 4, comma, and then the partial derivative with respect to y is negative x. And we set that equal to 0, comma 0. Any questions on that? Okay, what's the next step? If we have a vector equals 0, 0, what do we do next? So what do we do next if we have a vector equals 0, 0? L'Hopital's is a good guess, but that's really for limits when you have a 0 divided by 0. Very different. What you do is you set each component equal to 0. So if a vector is 0, 0, then the first component is 0 and the second component is 0. So we get 2x minus y plus 4 equals 0, and negative x equals 0. So here's a suggestion. You have 2 equations, and when you ever have 2 equations and you got to solve, this happens often, focus on the easy one. Don't focus on the hard one. What does the easy one tell us?
X equals 0.
X equals 0. So we know x equals 0. So now that we know x equals 0, we can take x equals 0, put that into the hard one. Now 2 times 0 is 0, so you just get minus y plus 4 equals 0. So give me a critical point. you tell me the critical point? Yeah, 0, 4. Okay, and that wasn't too hard, was it? Okay, imagine, by the way, if, we threw in, instead of a, x squared, making an x to the 5th, maybe add a sine of y and a cosine of x. You won't even have a chance of finding the critical point. So it's easy because I gave you an easy example. But I want to let you know the hard part of this is not the calculus. The hard part is the algebra. Even though this algebra was easy, still, I thought the calculus was 1 line and the algebra was 3 lines. And that's typical. So I want to give you that big warning, is that the algebra can be absolutely brutal sometimes. This wasn't too bad. Okay, and by the way, we should also just note, when does the gradient not exist? Hint that it's an easy question in this case. So when does a gradient not exist? Because those are the 2 choices, right? Yeah, but in this example, hint is it's easy. I don't see y'all jumping in. It's really easy. So when does a gradient not exist? No, 0, 0, yeah, no problems. I can plug in 0, 0 and I will get 4, 0. That worked. Do you agree? Okay, the answer is never. Gradient always exists. Negative 2, 2 is fine. Negative 2, 2 gives you a negative 4. That would be 0, 2. No problem. Yeah, the answer is the gradient always exists. But you should always check that, because in the definition, the gradient is undefined, means that that could be a critical point. Okay, this particular example didn't have an undefined gradient. The ones that do often are really messy and ugly. So didn't do one of those. Any questions on critical points and finding them? Okay, now let's see if you can remember, why did we care about critical points when you did first quarter calculus? What did they help you with? Applications, but what do they find? Why are they important? When we're looking for something, we're looking for the critical points.
Concavity?
Concavity is a good guess, but that was the second derivative, remember? There we go, max and mins. Yeah, so we're looking, if you're looking for relative max and mins, or local max and min, whatever you want to call it, then those happened at the critical points in first quarter calculus. Do you remember that? I hope. That was a big deal in calculus. So now it's time for talking about, first, we need to say what is a max and what is a minimum. So let's go to the definition and we'll see how that works. So let's suppose we have a continuous function, f of xy, on an open set containing AB. Okay, then if there exists a disk centered at AB such that f of AB is greater than f of xy for all xy in the disk, then f of xy has a local maximum at AB. Okay. Oops, I forgot to change this. Actually, max. So we also say that f of AB is the local maximum value. So I'm going to just show you a picture. And the cool thing is, I was like, I need an example. Do you recognize this picture?
That's just what you get when you turn on CalcPlot 3D.
Exactly. This is such a fault on CalcPlot 3D, and I'm like, this is like perfect. So I guess Paul, who wrote this, thought about that and realized this was a good one for that example. Okay, my guess is I don't have to do a lot of explaining to tell you where the local maximum are. How many local maximum do you see? Yeah, there's two of them. Okay, and the reason why I say this guy right here is a local maximum is I can take a little tiny disk near that point, and around that disk, if I just look this spot, then that point, that value of z, is the highest point in that little area. Does that make sense? Okay. So for example, I always like to give Tahoe examples. If you're on the top of Mount Talak, are you at a local maximum when z is the elevation and x and y are latitude, longitude? Are you at the max? Are you at a local maximum if you're at the top of Mount Talak? Can you tell me? Okay, the answer is definitely yes. Okay, that does not mean you are at the highest point in all of Tahoe. Okay, because Mount Talak is not the highest point in all of Tahoe. Okay, so did anyone know where the highest point really is? You got the idea of it, but your spelling is really bad. It's Freel Peak, Freel. Yeah, so Freel Peak is the highest point, but the top of Mount Talak is still a local maximum. Does that make sense? Okay, we have many local maximum in Tahoe. Okay, I think in Kansas they may have none. It's just one big flat spot, or maybe everything is local maximum because we have a greater than or equal to. So I guess Kansas, everything might be local max. But in Tahoe, Talak is definitely a local maximum. Is Freel a local maximum? The top of Freel, which is the highest mountain in our area. Is that a local maximum? Definitely. Definitely. That's still a local maximum. Freel is a local maximum because if you're standing at the top of Freel and you draw a circle that might be, I don't know, 100 meters, you're at the top. Okay, in that circle, who cares about the rest? All you care about is your little local circle. Any questions on that? Okay. Yeah, and by the way, local maximum and relative maximum, those are exactly the same. It's just English, so synonyms for the same word. That happens. Local and relative, same thing. Okay. I do want to let you know this can get you into big trouble. Because if you're looking for the highest point and you found your local maximum, did you find the highest point? Okay, and the answer is not necessarily. Sometimes you have, sometimes you haven't, right? If you're standing, I don't know, on the top of Round Mound near Nevada Beach, you may feel like you're at the highest point, but you're not even close. Does that make sense? Okay. Do you know where that puts you into real problems in the real world? And I'm going to say computer science real world. I think I'm going to adjust this because I think that might work. Let's see. What if I put a 2 here? No, that didn't work. So do you know where it's going to cause you problems in the real world? Okay, in the real world, let's try. Okay, so did that work? Nope, didn't work. I was trying to change it slightly to give you the real world example. Okay, in the real world, you're often interested in the true maximum. And what you'll use is what's called gradient ascent or gradient descent. And what that means is if you just randomly grab a point and then you go in the direction of the gradient. So if I'm over here and I go in the direction of the gradient a little at a time and go and go and go, where am I going to end up?
At the relative peak.
Yeah, I'm going to end up at the relative peak. So here's where it gets you into trouble. Let's suppose this peak was higher than this peak. So you're going to use this gradient ascent and you're going to end up right here. And that is not the biggest spot. And you're going to end up with a point that, yeah, it's higher than where you started, but may not even be close to the best solution. Does that make sense? If high means best solution. So that's a big problem in computer science, by the way, is you got to think about if you're going to be using this gradient ascent idea, which means go in the direction of the gradient until you get to the top. You're at the local maximum, but you're not necessarily at the highest point in the whole place. Okay, so now that we have that definition, I'm going to quickly go through local minimum because nothing really changes. Okay, let me see just a minute. Okay, oh yeah, just to let you know, if f of ab is greater than or equal to f of xy for all xy, none of this disk stuff, then f of xy has a global maximum at ab. Okay, and f of ab is the global maximum. That's a typo. Is the global maximum value. Okay, and then for minimum, exactly the same thing, except it's less than instead of greater than. So there exists a disk centered at AB such that f of AB is less than or equal to f of xy for all xy in the disk. Then f of xy has a local minimum at AB. And then we say f of AB is the local, that should be minimum value. So let's take a look at that picture again. Do you see, does this particular surface, does it have a global minimum? I'm sorry, a local minimum?
I would suppose so.
Yeah,
There's
2 of them, here and here. There's 2 local min. Again, once you understand local max, local min is just upside down. That's all it is. Any questions on that? Okay, so now I have a question for you. Let's
Can you go back to the definitions?
Sure.
Yeah, thank you. That's good.
Okay, so I have a question for you. In first quarter calculus, when you wanted to find a local max or local minimum, what did you do? How did you make that happen? So first quarter calculus, think about, October. Yeah, you use the first. Well, we use the first. Okay, if you just wanted to find out where they could be, not to decide whether it is a local max or min, but just where the values could be. What did we do? Do you remember? So what'd you do to find where the max and mins could be? Yeah, we took a derivative and we set the derivative equal to 0. And then we said that if you're going to have a max or a min, that's where it's going to be. And then sometimes you could go wrong. You can get an inflection point, right? Okay. You can get some weird stuff going on where it's not a max or a min, it's an inflection point. So the good news is we basically follow the same process, but there's an extra piece. Okay. Oh, I guess I should note this. Absolute and global mean the same thing, just like relative and local mean the same thing. Okay, so here's the theorem, okay? And I call it, this is not the official name, but it's what I call it. I call it Fermat's not last theorem. Do you know why I call it that?
It's not his last theorem.
Yeah, well, do you know what his last theorem was?
Solve.
What do you know what Fermat's last theorem is?
I know it's like deceptively simple seeming, and that it wasn't solved until like 1994.
Yeah, yeah. So, yeah, and I was actually, the funny thing, I was one of the only ones in California that understood the proof. It was a 350-page proof, and I read it just to let you know how brutal it was. So most people don't believe Fermat actually proved it. So it's a proof. Basically, it's an extension of the Pythagorean theorem, and I'm not going to get into it. But Fermat also proved before he thought he proved that other theorem, which I think he didn't. He proved this following one, which is very important, and that is let f of xy be a continuous function on an open set containing AB. Then all local extrema occur at critical points. Okay. Have we seen that before, haven't we? In one variable calculus, right? If you want a max or min, they always occur at a critical point. Well, Fermat is the one that came up with this for functions of two variables. Okay, which means that if we want to find out where the max and min might occur, the local or relative max or min, we take a gradient and we set the gradient equal to 0. And that guarantees that we will have all the candidates for the relative max and relative min. Any questions on that? Okay, so that's a big theorem. Again, today's not a proofs day, but it's important that you understand the theorem. So if you have questions, please ask, and we're going to use it in a big way. So here is an example. And that is the following. Find where the relative extrema could lie. F of xy equals x squared minus xy minus 2 at y plus x minus 1. So I'm going to use Fermat's not last theorem. So what do I have to do?
Find the gradient, set it to 0.
Yep, we take the gradient. So grad. Okay, as I mentioned last time, the gradient is the biggie. Okay, you definitely, if you are even a little confused about the gradient, please stay and come to my office hours and I'll help you with it, because the gradient is the big topic for the whole week. So the gradient of f is equal to, and what is it in this case? So what's the first coordinate or component of the gradient? What's the I component of the gradient? Yeah, so you take the partial derivative, partial with respect to x of x squared is 2x. Partial derivative with respect to x of xy is y. Okay, partial derivative with respect to x of negative 2y is 0. Partial with respect to x of plus x is 1. And constants always go away. And then we do the same thing for y. Partial with respect to y of xy is x. Partial derivative with respect to y of negative 2y is negative 2. Whoops, that goes here. So minus 2. And the x minus 1 goes away. They don't have y's. And I set those equal to 0, comma 0. Any questions on that? All right, so now to set those equal to 0, 0, we can set each individual equal to 0, 0. And I'm going to go through the algebra fast because I'm going to assume you know how to do algebra. If x minus 2 is 0, what's x? What's
Would it
x?
be 2?
Yep. And x is 2. So we get 4 plus y plus 1 equals 0. Or y plus 5 equals 0, so y is negative 5. Okay, is the only point where the relative extrema can lie. Any questions on this example? Okay, now comes the next one, and there's a definition. So it's time to start thinking about finding out whether it's a max or a min. Do you remember how we did that in first quarter calculus to find out if a value of x is a max or a min? Or is a value where the max or min occurs? Do you remember how you did that in first quarter calculus? What did we use to decide, to determine max or min? Yeah, so there was a first derivative test, but I want to focus on the second derivative test because that's the only one that actually applies to what we're doing today. There was a second derivative test. All right, what's the problem with the second derivative when we're doing functions of two variables? Is there a second derivative? Okay, it's not fun. It might be fun, depends on what you think is fun. Okay, so here's the key. It was a trick question. There is a second derivative. Remember when we said there was a first derivative, but we had to make it a vector, and we called that the gradient? Same idea. There's a second derivative, but we're going to make it a matrix. And here's the definition. Let f of xy be twice differentiable. Then the Hessian, let me make that in red. So then the Hessian of f of xy is the matrix. And unfortunately with Google, you can't really make matrices nice. So I made it a table. fxx, fxy, fyx, fyy. And that's a matrix. And that is often considered the second derivative. But just like before, for first derivative, we had to make it a vector. Now we make it a matrix. Any questions on the Hessian? Okay. So now we're doing matrices. And again, we're only going to just do a little bit in this class. This gets very deep. Okay. You can talk about, higher order derivatives also. You can talk about higher order functions. You can talk about functions of 5 variables. And if you want to write down the Hessian for a function of 5 variables, you'll have a 5 by 5 matrix. So it gets pretty intense. We're just going to handle these 2 by 2s. So let's see if you can find the Hessian of f of xy equals 3x e to the 2y minus x to the 4th. Let's see if you can find the Hessian. And I'll pop in a little table because it'll be a table, a 2 by 2. Or a matrix, really, but it's all I can do with Google. So what goes here in the top left? Or sometimes we call that the 1, 1 or the XX component. Okay, it might help to get it set up. F sub x is equal to, partial with respect to x is 3e to the 2y. And then minus 4x cubed. Because you can't do the second derivative without the first derivatives. And f sub y, so I'll do the first derivatives for you. F sub y equals, and then we get 6xe to the 2y. And then the minus x, oops. And then the minus x to the 4th goes away when you take a derivative with respect to y. So that helps. Okay, so if we want the xx coordinate, we take another derivative with respect to x of f sub x. The 3e to the 2y goes away. And the derivative of negative 4x cubed with respect to x is negative 12x squared. Okay, how about fxy? Yeah, that's going to be 6e to the 2y. Because I take the y derivative of the x derivative. And notice there's no y's on the 4x cubed. That goes away. Use a chain rule and you get a 6e to the 2y. Why do I not even have to think to get fyx? Okay, it's always going to be the same of f as fxy for all nice functions. In our class, all functions are nice. So 6e to the 2y. And then fyy, that one we have to do a little work on. That's going to be 12xe to the 2y. Any questions on that? Okay, so the next is find the determinant of the Hessian. Who remembers how to find the determinant of a matrix? 2 by 2. So how do you find the determinative matrix? Yeah, you multiply in the diagonal and subtract, actually. So we're going to take AD minus BC. So let me write that out. I'll kind of write it the slow way. Negative 12 e to the x squared. Oops. Oh, sorry, negative 12 x squared times 12x e to the 2y. And then minus, and then we're going to have a 6e to the 2y squared. And notice there'll always be a squared term there because the diagonal, these off diagonals will always be the same. So when you multiply, you just get the square. And I'm not going to bother you with doing the algebra, but you can do the algebra. Any questions on this Hessian? All right, so let me tell you another biggie, and I'm going to give you a little history. Okay, imagine, imagine you're hanging out with Newton, right? And you got to go to work. Are you going to take your car?
I think they had cars in his time.
Right. So how are you going to get to work? Let's
Horse.
say it's 5
by
miles.
Horse or by walking.
Well, you have a little money, so you can take a horse. Yeah, you can take a horse. Okay. So here's a big definition, and it came from. So I'm not just saying some off-topic thing. It really comes from that, and it's called a saddle point. Because hopefully, maybe you know, maybe you don't know, is that most people don't sit on a horse without putting a saddle on that horse. Okay, it's just part of horseback riding. And so in those days, they had a saddle, and it works really well for what we're doing. Okay. So AB is a saddle point of f of xy. If the gradient of f is equal to the 0 vector, but AB is not a critical point, I guess I should say, let's say not a max or min, relative maximum or min. Of f of xy. So the nice thing is this picture comes in again. And this is basically a saddle right here. So if we look at the origin, you can go along this way and we get, do you see this parabola here? So it looks like the origin, if you just look at this parabola, then the origin looks like a minimum, doesn't it? Like a relative minimum. Do you all agree? So if we look at this parabola, it's the bottom of that parabola. Any questions on that? On the other hand, we can actually go from below and come up and then down. And it's the top of this parabola. Can you see that? So let's make it so you can see it better. That's about right. So you can see that you start down at the bottom, you go up to the origin, you come back down to the bottom, and now it's the top. Well, look, it's a minimum and it's a maximum. So if it's a minimum and a maximum, is it a minimum or is it a maximum? What do you think? Right? I use one curve and I got a minimum. I use another curve, I got a maximum. So what is it? It's a saddle point. Okay, so that's what a saddle point is. And if you've been horseback riding or played around with a saddle has a saddle point right in the middle. That's where you sit. Because when you're sitting, your legs are the parabola, where the top of the parabola is your tush, but then front and back it goes up on that saddle, right? So in a way, horse's head would be around here. You're sitting like this with your legs coming down like that. You're holding onto the saddle like that, and the back is keeping you from falling off the horse from behind as the horse runs. So that point is the saddle point. Any questions on that? Okay, but also note about that point, if I take that curve and I look at the gradient, I get 0 because notice that at that point, if you look at the tangent plane, it gets quite interesting. It's just horizontal, and the gradient becomes 0. So it turns out there is no maximum up or down kind of direction. It's just the top and the bottom at the same time. So that's what a saddle point looks like. It looks like where you sit on the saddle. Any questions on that? Okay, so here comes the big second derivative test. Let me put that in red. So do you remember the second derivative test in first quarter calculus? Took a second derivative. If the second derivative was positive and the first derivative was 0, what did you say about the function? Yeah, it's min. And if the second derivative is negative and the first derivative is 0, it's a max. So we're going to have the second derivative test, but now the second derivative has to do with this Hessian. Okay, so let f be a twice differential function, such that the gradient of f of AB is 0, because if you don't have that, you can't get a max or min. And let D be the determinant of the Hessian matrix, evaluated at AB. So the formula for that would be fxx, fyy, minus fxy squared, evaluated at AB. Then, I guess I should write D equals. Then, if D is positive and fxx is of AB is greater than 0, then f has a local minimum at AB. Okay, again, I'm not going to be able to prove all this, but hopefully you can trust me. Okay, if, oops, I made a mistake here. This should be, yeah, this is, no, that was right. But I forgot the number 3. If D is greater than 0 and fxx is negative, then D have a local maximum at AB. If D is negative, then F has a saddle point at AB. And if D equals 0, you're out of luck. You know nothing. The test failed. Do you remember that in first quarter calculus for the second derivative test? If the second derivative was 0, you're out of luck. I don't know if you remembered that, but that was the truth. Okay, so here's how this works. Any questions on this idea? On this theorem? There's a big theorem. A lot of details. Okay, locate and classify the relative extrema of f of xy equals 4xy minus x to the fourth minus y to the fourth. All right, well, how do we find out where the possible extrema are? What do we have to do? First step. Starts with a G. Take the gradient. Take the gradient of f. And that is equal to, let's take the derivative with respect to x. You get 4y minus 4x cubed, comma. And if we take the derivative with respect to y, we get 4x minus 4y cubed. And we set that equal to 0, 0. Any questions on that? Okay, in this case, there isn't one easier than the other, but I'll just use the first one. I could say 4y equals 4x cubed, or y equals x cubed. So now I can plug that into the second one. And I have 4x minus 4y cubed, which is 4y to the 9th. 4x to the 9th. So this is the first one we actually have to do some work. Equals 0. So that means x to the 9th equals, or let's say x minus x to the 9th equals 0. And that means x times 1 minus x to the 8th equals 0. It's a little factoring. So what is x?
Likely 0. Well, actually, definitely 0.
X can be 0, but what else could it be? Not definitely 0. 0 is one possibility for x. Could also be -1. It could also be 1. Because 1 minus 1 to the 8th is 0, and 1 minus -1 to the 8th is also 0. So I got 3 different x's it could be. So now we can actually get our points. So our points, if x is 0, y is x cubed. So 0 cubed is 0. If x is -1, y is x cubed. So that's -1 cubed is -1 in this case. And if x is 1, we get 1. Any questions on that? Okay, so now what we do is we've got our 3 points that are possible. Do we know which is a max and which is a minimum? Not a chance. We have no idea. So what we do is we find the determinant of the Hessian. So I'm going to do this pretty fast because we don't have much time. But determinant of the Hessian is equal to, so we take the, actually, let me go d of 0, 0. One at a time. So again, if we look at f(xx), then that's going to be 12x squared. Plug in 0, you get 0. Similarly, fyy is 0. fxy is 4. And fyx is also 4. So we get 16. And it's a minus because it's fxx, fyy minus fxy x squared. So it's minus 16. And notice that d of 1, 1. Okay, that one's going to take a little work. So now we take the derivative again. The derivative fxx is going to be -12x squared. And that's going to be -12. And then fyy is also -12y squared. That's also -12. And then minus. And we look at fxy, that's 4. And then fyx is also 4. Well, it's just 4 squared, of course. And all that matters, I don't care about this number. I care about is it positive or negative. And you see that's greater than 0. And in fact, -16, I hope you all know, is less than 0. Okay, now we do the same thing. But let's plug in -1, -1. Okay, so now let's take a look. It was a -12 times -12. And then we still get -4 squared. Turns out to be the same when you do it. And that's positive. Okay, well, first thing is that if D is negative, what can we say immediately? Based on our theorem. If D is negative,
F has a saddle point.
yes, that's a saddle point. If D is positive, we have more work to do. So we also have to look at fxx of AB. And fxx now, remember, is going to be -12x squared, right? And if I plug in -12x squared, I get a negative value. Any questions on that? So what do we say? It's a local maximum. Okay, I'm going to leave it to you to do the last one because I don't have much time left and I want to get to global extrema. So the nice thing for global extrema is it's step by step. Step 1, determine the critical points. Step 2, evaluate F at each of the critical point. Step 3 is determine the maximum on the boundary given the domain. Step 4 is the global maximum is the maximum from steps 2 and 3. And step 5 is global minimum is the minimum from step 2 and 3. Notice you don't need to use the second derivative test. So I'm going to quickly do this. So I need to find the critical points. To find the critical points, what do I have to do if I want to find an absolute extrema of this function? First step, it's the biggie in this whole week, is the gradient. Yeah, we take the gradient of f, and that is equal to, with respect to x, is 3x squared minus 3y. With respect to y, is -3x minus 3y squared. Okay, again, step 1 was to find the critical point, so I set that equal to 0. Okay, and then I solve that. And what do you get? So just quickly, certainly 0, 0 works. That hopefully you can just eyeball it. We can see y is x squared. If y equals x squared, then we know x is negative y to the 4th power. Oh, if y is x squared, sorry. Y is negative y to the 4th power. Any questions on that? So if y is negative y to the 4th power, then what do we get? Or maybe I need to quickly write this out. So y equals x squared. From the first one. And then we plug in, and it's, sorry, x is, I can divide by 3. X is equal to negative x to the 4th. Can you give me a number whose 4th power is negative what you started with? -1. Yeah, -1. Yeah, 0 we already got, so there's no reason to do 0 again. So -1 to the 4th, take a negative that, you get back to -1 again. Okay, and that's the only one you'll get, by the way. And then if y is x squared, then y is 1. Okay, I want to determine the maximum on the boundary. That's step 2. So to go to the boundary, I don't have time to finish because we're out of time, but I'm just going to explain how to do that. So if x is between -2 and 2, y is between -2, that means I plug in x equals -2 into the equation. Find the max for the y. So x is -2, y is whatever that max will be. I do the same thing with x equals 2. And then I do the same thing with y equals -2. I do the same thing with y equals 2. Okay, and I'll get 4 different numbers. So I'm just going to say P, Q, R, and S. Okay, whatever those are, plug in to the original function. Zero comma 0, -1 comma 1, P, Q, R, S, and the biggest will be the maximum and will be the global maximum. The smallest will be the global minimum. I don't like to go too much and I'm overboard already on my time. So let me stop. And I'm going to stop the recording.